Hello, everyone. My name is Gregory Nero. I'm a fifth-year optical sciences PhD candidate at the Wyant College of Optical Sciences at the University of Arizona. In this video, I'm going to show you how we here at the Takashima Advanced LiDAR and Display Lab use a digital micromirror device to diffractively steer a laser beam. We'll review what a digital micromirror device is, how it is typically used, explain the basics of the diffractive laser beam steering technique we've developed, and show you an in-lab demo of the system. Let's get started. A digital micromirror device, or DMD, is an array of individually addressable micromirrors developed by Texas Instruments. Here is a picture of what a DMD module looks like and an up-close view of a few of the mirrors. The red boxed region is the active mirror array and contains over 400,000 individual mirrors. Each mirror is about 11 microns on a side and can rotate plus or minus 12 degrees with respect to a flat state along the mirror diagonal. DMDs are traditionally used in projector display systems. A light source illuminates the DMD surface, and the on mirrors, which encode the image information, will direct that light through a series of projection optics out to a screen for us to view, and the off mirrors will direct light to a beam dump or a light absorber. The micromirrors here are only used in a binary on-off modality. Either the mirror is on and the light is channeled to a screen, or the mirror is off and the light is channeled to a light absorber. But what about the in-between states? What if we could use the mirrors while they were transitioning from the on state to the off state? A DMD micromirror will take about 2.4 microseconds to transition from the on state to the off state. This is pretty quick. However, if we use an even faster laser pulse on the nanosecond timescale, we can precisely control when a laser pulse will see the mirrors in their transition. A nanosecond scale laser pulse will effectively see the mirrors frozen in a particular angle. So how can we use this? Depending on when the laser pulse arrives at the transitioning mirrors, the pulse will see a certain phase profile. Consider 3 different times along the mirror transition, T1, T2, and T3. Here, we show the wrapped phase of the wavefront across a portion of the mirror array for 3 such cases. The big idea here is that if we get the timings just right, we can create phase profiles across the mirror array, which leads to constructive interference into specific diffraction orders. The DMD therefore acts as a programmable phase grating. This is the fundamental idea of diffractive beam steering. Before we get into lab, let's review what the optical and electronic layout of the system is. A laser pulse, whose angle of linear polarization is controlled by a half-wave plate, illuminates the DMD after passing through an iris, polarizing beam splitter, and quarter-wave plate. That light interacts with the DMD while the mirrors are transitioning before traveling away from the DMD and out to a screen. Here we use the polarization optics to increase the power efficiency of the system, but you could just as easily use a simple 50-50 beam splitter to normally illuminate the DMD. The electronic architecture utilizes an Arduino DUE, which sends trigger signals to both the laser to tell it when to pulse and to the DMD to tell the mirrors when to start moving. By controlling the timing of these pulses, we can control the angle at which the laser sees the mirrors, which controls the phase profile and slope of the blaze grating, which controls the diffraction order that we steer to. Now that we've reviewed the theory and explained the setup, let's get into the demo. Okay, so now we're in the lab. Right now, we're looking at the screen at which the DMD is steering to. The DMD is currently off. When the DMD is off, the mirrors are in their flat state. The beam of interest is right above the line marked flat. You'll notice that there's other dots surrounding that beam. This is from the diffractive artifacts of the micromirror array. Okay, so now the DMD has been turned on and the mirrors have been switched to the off state. If we ask the mirrors to switch to the on state, we'll see that the beam is steered to the on state. And we can go back and forth like this. This is traditionally how this device is used, in a binary on-off modality. Next, I'm going to show you 2 demos in which we can diffractively steer the laser beam between these on and off states by synchronizing the timing of the laser pulse and the transitions of the micromirrors. In this first demo, we continuously diffractively steer the laser beam between the on state and the off state. We do this by controlling the timing between the mirror transitions and the laser pulse. Each diffraction order corresponds to a specific timing delay between the mirror transitions and the laser pulse. We see that each diffraction order exists at a specific angular location or spatial location on the board. This is dictated by the grating equation. The spacing and number of diffraction orders will depend on the pixel pitch of the device and the wavelength that you're using. In this next demo, I'm going to show you how we can steer to a specific diffraction order on demand. We've numbered on the screen 1 through 9. Each of these numbers corresponds to a diffraction order location that we can steer to. Each number, therefore, corresponds to a specific delay between the mirror transitions and the laser pulse. Right now, we're steering to 8. If I ask the system to steer to 2, it will change the delays and steer to 2, or to 4, or to 6, or to 1, or to 9, or to 7, for example. Thank you very much for watching this video about diffractive laser beam steering with digital micromirror devices. If you want to learn more about how we use this technique for a bunch of different applications like LiDAR and display, you can check out some links in the description. Thank you very much for joining us, and we'll see you next time.